Okay, good morning everybody. Unit number 4 and module 4. So in this today's lecture, I'll be going over very important type of processes called as stationary processes. And we have various degrees of stationarity starting from the first order process, second order process, and so on till the nth order process. We define what is meant by stationarity of a random process in the strict sense. What is it? The stationarity of a random process in the strict sense. Okay. Consider the concept of stationarity. Consider the following is a random process consisting of random variables from the time t1 till tn. Each of these is individually a random variable, and the type of random variable could be of any type. Probably if you have known a uniform distribution or a Gaussian distribution. So depending on the type of the process, these variables can be individually different types of distributions. Okay, not that all of these are similar type of distributions. They could be different. Now, so each of these variables are in generally are very different from each other, and because of this randomness, they do have a different statistics. So if you know the meaning of the statistics, this means these are some kind of measures that are used to describe a random variable. For example, this could be the mean of a random variable, the variance of a random variable is also called the second moment of a random variable, and typically every higher moments. So these are all the statistics of a random variable. The meaning of the stationarity is not is very common among usage. When do you call something is stationary? Yes. Okay, think about this like this. What is the opposite meaning of stationary? Okay, stationary means stillness, or something that is not changing over time. Something that doesn't change from one time point to the other time point. It is stationary. It is said to be a stationary process. Okay. Now, the opposite of stationarity are non-stationary or time varying. So in this context, we use the word stationarity to mean a stationary random process. So we can define, in general terms, we can define stationarity as of a random process as the process in which the random where the properties are some kind of statistical properties of the random variable doesn't change over time. They are all somewhat similar to each other. In that sense, a process can be called as a stationary random process. Okay. Now, if you see the statistics, we calculate the mean of a random variable at the time t, as the integral of minus infinity to plus infinity of x times the PDF. So in calculating all of these statistics, the common function that we use is the PDF. Okay, so remember this PDF has got significance and we will use it again and again during the rest of the slides. Now, define what is a first order stationary process. A random process x of t is stationary to order 1 if the probability density function or PDF doesn't change with time. So what that means? The PDF is same for all the time points. So the important condition to satisfy for first order stationarity is that the PDF of one single random variable at any time t should be equal to the PDF of the random variable at some other time point t plus tau. Okay, so that means at the point the random variable at the point t and the random variable at the point t plus tau both should have a same PDF. In that sense, we can call, if that condition is satisfied, we can call that random process to be a first order random process, first order stationary random process. Okay, let's move on. Now what is similarly defining along the same lines, what is a second order stationary random process? Second order stationary random process. So a random process x of t is stationary to order 2 if its second order density function, which is given as fx of x1 comma x2 at the points t1 and t2. So on the left hand side is the joint density function of two random variables x1 and x2 at the times t1 and t2. So this is basically x1 of t1 and x2 of t2. If the joint distribution or if the joint density function of these two random variables is equal to the PDF at the time points t1 plus tau and t2 plus tau, then that process is said to be a second order stationary random process. So here the second order means that we have to consider a joint PDF of any two random variables. So now let us look at this picture. Let us fix tau is equal to 1 in the above equation. So what do we get here? Fx of x1 comma x2 colon t1 comma t2 should be equal to fx of x1 comma x2 colon t1 plus tau 1 comma t2 plus 1. Okay, now let us consider the following two random variables as an example, x of t4 and x of t5. Okay, now if I shift these two random variables, if I shift whatever this axis, vertical axis, by 1 unit to the left hand side. So I'm going to do that. If I shift this one unit to the left hand side, I get the variables x of t3 and x of t4. So according to our definition, these two random variables x of t4 and x of t5 should have a joint density function which should be equal to the density function of these two random variables, that is x of t3 and x of t4. Okay, similarly we can take any number of pairs, and all these pairs should have the joint PDF same as any other pair of random variables. Then we can call that random process to be a second order stationary random process. Okay, so the pairs could be anything. So any two random variables must have the same joint PDF. If this condition is satisfied, then that random process can be called as a second order stationary random process. Now, what is an nth order stationarity of a random process? When do we call a random process to be n order stationary? So similarly, this is true when the nth order, the n joint distribution function at the times, the joint density function at all the times points t1 so on tn is equal to the joint distribution function of the random variables at the points which are shifted by tau, and for all values of tau. So this means that suppose in a random process we have n number of random variables, and if you take the joint distribution or the joint density function of all of these n random variables, it should be equal to the random variables which are shifted by tau number of units, and this tau can take any value, 1, -1, or could be any all real values. If this condition is satisfied, then the random process is said to be a nth order stationary random process. Now, when this condition is satisfied for a process, that means if the n number joint distribution is same as the shifted joint distribution, then that process can be called as stationary in the strict sense. In the strict sense, it is a stationary random process. Now, well, this nth order stationary random process and nth order stationary random process x of t is also n-1 order stationary, n-2 order stationary, and down below second order stationary and also first order stationary. That means if the process is nth order stationary, it is also n-1 order stationary, n-2 order stationary, so on first order stationary. So this nth order stationarity is a very strong condition. Normally, it is very impractical to see such kind of a random process in nature. To prove that the nth order stationary random process is also n-1 stationary, consider the following integral of the joint PDF of all the time points from t1 to tn. Now if I integrate this PDF over the random variable xn, this xn goes away in the integration. What I'm left with is the PDF only from x1 to xn minus 1. So that is for the time points t1 to tn minus 1. So we can go on integrating the obtained functions to come at the second order and also the first order PDF. Okay. Now we talked that the nth order stationarity is a very uh, impractical random process that could not be found in real world process. So what are the processes that are really found in nature? These are generally of the type second order. Usually we don't need to go more than the second order stationarity. It is itself sufficient to describe any real world, almost all real world processes. Take for example, voltage from a AC generator or a thermal noise. These are the random processes which normally we do not go beyond calculating the second order stationary. Okay, in this, even among second order stationary random process, still we have to have complete knowledge of the probability, the joint probability density function fx of x1 comma x2, and this is normally unavailable beforehand. So take for example the examples we have seen before. We have generated the data ourselves and we have generated the data matrices. However, using only a finite number of trials, we could not have, we probably could, we have not seen, probably we have not seen some outcomes which are already in that set. Therefore, this is not readily available. Even this function is not readily available. Hence, we go for what is called as an autocorrelation function. So this autocorrelation function is denoted as capital R of t1 comma t2. I'll go through this function in a few slides, and this is the function we normally use to describe the statistics of real world processes. Normally, we don't even use the second order stationarity also, and many processes that we come across in real world normally are described by only up to the autocorrelation function. Now, coming to the summary of some of the statistics of random process, we have the mean of a random process, which is the eta of t is equal to the expectation of the random variable at the time t, and this mean is a function of time. Similarly, we have the variance, which is the second moment or the expectation of x of t minus eta of t whole square, that is a average of the square of these values, and it is calculated as the integral of whatever is within the square bracket times the PDF. Okay. Similarly, now define the autocorrelation function as expectation of the product of two random variables at the time t1 and t2. Okay. Now this is calculated as whatever is within the square brackets, that is x1 comma x2, the integral of x1 comma x2 times the joint PDF of these two random variables. Okay. Now the autocovariance is similar to the autocorrelation function. It is simply obtained if we take out or we subtract the mean of each of these processes from them and then calculate the autocorrelation function of these zero mean random variables. Now this can be proved and is equal to the autocorrelation function itself minus the product of the two means. Okay. Now this is one example of calculating an autocorrelation function. So find the autocorrelation of the voltage V of t is equal to R capital bold R cos omega t plus phi. Here please note down that the random variables are usually shown as bold letters. V is a bold letter, R and phi are bold letters. And we have to assume that these R and phi are independent to each other, and the random variable of the phase phi is a uniform random variable in the interval minus pi comma pi. And we can calculate. I'll not be going over the calculation of these again, but we can calculate this autocorrelation function at the time points t1 and t2 as equal to a function which is only depending on the difference of these time points t1 minus t2. So whatever the values of t1 and t2 we take, this autocorrelation function only depends on the difference of these time points. For example, when t1 is equal to 1 second, t2 is equal to, let's say, 2 seconds, this autocorrelation function only depends on the difference of these two, that is t1 minus t2 is equal to 1. Similarly, if you take t3 and t1 is equal to 3 seconds and t2 is equal to 4 seconds, still our autocorrelation function is the same. So this autocorrelation function doesn't individually depend on what times we use here, but they are only dependent on the difference of these time points. Okay. In the next class, I will discuss what is a wide sense stationary process and where do we use normally in the signal processing. And by the way, these become the very practical type of random process we see in nature. Okay, so let us end this lecture here.